project, we're doing complex Newton. And so it's just like last week's project where we did the Newton's method. However, this week's functions include the letter I, or the imaginary number. But I first want to assure you the basic concept of the Newton method remains the same in this project. We're taking this line where we take z, the value of the function at z, and the value of the derivative at z, and we repeat this step over and over and over until we eventually center around a value that's our root. So where this project differs from last week's project is that we're going to have a function with a bunch of different roots in the same general area. And so if you might imagine, depending on where we start along this function, performing the Newton method is going to give us a different output root. So if you imagine, if I start here, I might end up getting this root. Or if I start here, I might end up getting this root. Or if I start here, I might end up getting this root. And so that's the basics of this week's project. We want to figure out, based on where we start on our function, which root we're going to end up getting. And we're going to use a function that includes I. That's all that is. And so if you take a look here, and if you guys want to follow along, this is on page 2 of the project documentation. The very first thing we do is we want to get a bunch of different starting points to test. And so we create these matrices x and y, and these are going to contain all these starting values, right? And they're pretty large matrices. As you can see, the step value is 0.0025. So these contain a sizable number of values. And what we're going to do is we're going to combine them into complex valued starting points by creating this matrix Z here. And each element of Z is equal to x plus I times y. So the very first element is going to be 0.15 minus 0.15i. And so we're going to have this matrix full of all our different starting points. And then the next thing we want to do is we want to perform the Newton's method with all these given starting points, right? And that's where this magical for loop comes in. And so the very first line of this for loop is 1 through max iter, and in the project I believe we're using 20 for max iter. That's just repeating this step 20 times, so it's going to get us decently close to the root. So it might not get us all the way there, right, because we're only doing 20 iterations, but it'll get us close to one of the roots. But the real magic of this for loop comes in is when we operate this for loop and we apply the matrix Z here. By doing this line here, by doing Z and then f of Z and then f prime of Z, including this entire matrix, what we're able to do is we're actually able to perform the Newton's method on every single starting point simultaneously. Because we're inputting this entire matrix. We're not just inputting a single value, we're inputting all these values into here at once. So this is a pretty cool thing, right? Not all programming languages are able to do this, but this is the cool part of MATLAB. We can take all our starting points and perform the Newton's method for each of them all at the same time. And then when we're done, we're going to get this matrix Z that's going to include the roots of every single starting point. And so that's cool, right? Once we get this step done, we're going to have the root for every single starting point. The next thing we need to do is we need to correspond which starting values correspond to which roots. And why are we doing that, right? Well, the final goal of this project is to produce something called a Newton basin. A Newton basin is just a really fancy graph that essentially says, I'm going to take a starting point, and depending on which root it ends up being, I'm going to give it a certain color. So if this starting point ends up going to root number 1, I'm going to color it blue. If this starting point goes to root number 3, I'm going to color it yellow. And essentially what you do is you create a graph of all the different starting points like this, and then you give them all different colors, and you end up getting these cool patterns and graphs and shapes. So that's all you're doing. So in this step 2, we need to correspond which starting points go to which roots, right? Because then in step 3, we can assign each starting point its own color. And then we can finally plot it. And so that's the entirety of this week's project. It's really simple. All we're doing is we're making a bunch of starting points, performing the Newton method on them, and then seeing which roots they end up going to. And depending on which roots they end up going to, we're going to give it a special color, and we're going to plot that. That's all this week's project is, so it's pretty simple. But just beyond this conceptual idea of the project, I want to go over a few other things that are going to be a little bit tricky. The first thing is, in this step here, we want to figure out which start values correspond to which roots. If you notice up here, we're only doing 20 iterations of the Newton's method. So that means we're not going to get close to the real root every single time. So before we even begin this whole process, we're going to use a built-in MATLAB function to find the exact roots of our function that we're going to use in order to perform the Newton method upon. And so that way we can figure out, oh, when we get a root that's somewhat close to an actual root, we can just say, oh, the computer was actually trying to find that. So this is just making our life easier because now we don't have to guess if we get some root that doesn't really seem to match up with anything else. So yeah, that's all that part is. And then also, we're going to have to do this, f prime of z. In this week's project, they want you to actually develop a function in order to calculate the derivative. And it turns out that's actually not going to be that hard. All you have to do is rely on the power rule. Essentially, all you're going to be doing is you're going to be taking the power and you're going to be moving it down to multiply. And so it's a little bit tricky, but you'll be able to figure it out. All you got to do is put the power rule into code. And so it's an interesting little side project. And then the very final thing you have to do is when we get these Newton-Mason graphs, we want to give them fancy titles. And the titles we want to give them are the function that they start off with. So if like the function that we found was like x to the fourth plus x cubed plus x squared, well, we want to make this into our title. And it turns out it's a little bit tricky because if you try and input this into a title of the graph, you're going to see something kind of weird. You're going to get something that looks like this. 1x to the fourth plus 1x cubed, right? And that's really stupid, right? We don't write math this way. We don't write these leading ones or leading zeros in some cases. So your job is to get rid of these ones and make the graph title look like normal math. And so, again, a little bit tricky, but if you tinker with it a little bit, you'll be able to figure out with no problem. And so yeah, that's this week's project. Not a big deal. I'll talk to you guys in the next one.